So, we need to talk about magnetic fields. So when dealing with magnetic fields, there's a couple of things that you need to keep in mind. First of all, that all magnetism is a result of moving charges, one way or another. A moving charge will create a magnetic field. So if you think about it, if you had a piece of wire, and you had that piece of wire with current, so current flowing through that long piece of wire, I end up generating a magnetic field because of that. Now, the direction of the magnetic field depends entirely on where you are located to that wire. So, in order to show the direction of the magnetic field, we're going to use what's called the right-hand rule. We're going to take our right hand, and we're going to put our thumb in the direction of the current, and our fingers will wrap around that wire. Now, the directions in which my fingers wrap around is going to give me the magnetic field. So if I put it in there, it's the direction of the current, my fingers wrap around. So if I were to look at it more three-dimensionally, current's flowing through there, it's going to wrap around like that. There's my magnetic field. Now the difference between magnetic fields and electrostatic fields, if you remember the appearance of an electrostatic field, I had a positive charge, okay, and that positive charge creates an electric field. It just moves out into space. It's radiating forever out into space. In the case of magnetic fields, my magnetic field always has to reconnect with itself or with another piece of magnetic material. Okay, so it's a complete system. It returns to itself. Okay, so that's what makes it a magnetic field. Cool? In the case of a bar magnet, if you were to look at a bar magnet as a magnetic field, north, south, we have field lines that go out of there and then will swing back to the southern end, okay, returning once again to itself. Now, if I introduce another bar magnet into the system, south-north, I do end up getting this situation, where the arrows go into the southern end of that magnet. Now, that's fine. It's the same thing when we're dealing with electrostatics. If I had a positive and a negative, these will radiate out and then radiate back into the negative, much in the same way these bar magnets are radiating out and returning back into the other magnet, into the other pole. Cool? So normally when we talk about magnetic fields, we talk about them being continuous and come back into themselves, or they intersect something else, where electrostatic fields continue to go on forever. Okay? And the other thing is that we need to know that magnetic fields are the result of moving charges. Now, in the case of a current, we put our right hand in the direction of the current, curl our fingers, and that gives us the direction of the magnetic field. Now, what about ferromagnetic material? If you talk about ferromagnetic material, you're talking about the exact same principle. Okay? Inside ferromagnetic material, you have your atom. In that atom, you have an electron circling that atom. Okay? So I've got my nucleus here. I've got an electron circling that. Well, moving charges create magnetic fields. I had a current here, which is moving charges, and that created a magnetic field. Now, in the case of ferromagnetic materials, that moving charge is spin orientation. It's a nucleus with an object circling around it, an electron circling around it. That electron represents the moving charge. Okay? So if we were to look at it, here's my atom, here's my electron. We end up generating a magnetic field that looks something like this. As a matter of fact, it will loop back onto itself, like that. Okay? So you're generating this magnetic field that's moving through, moving as a result of, or not moving, but you have this magnetic field because of that moving electron. Now, if you get a whole bunch of those with about the same spin orientation, you create what's known as ferromagnetism. You get iron, you get cobalt, and nickel. Those are, I think, the three primary ferromagnetic materials. And all that is because